Hi, let's do the last video on the wave nature of light, and we're going to look at total internal reflection and critical angle. Now, what's total internal reflection? Well, when light crosses from one medium to another, some of it gets reflected. And you may have noticed that, and I may have mentioned it in a video or two before, but we'll look at it in a bit more detail. When the angle of incidence is small, the reflected ray is very weak. You only faintly see it. But as the angle increases, it gets stronger and stronger. And so more and more light gets reflected rather than refracted. Usually when we draw our nice diagram showing refraction, we pretty much ignore the reflection part of it, because that just obeys the law of reflection. But as the angle increases, we start getting more interested in it, because we reach a certain point, which is called the critical angle, when all the light gets reflected and none of it goes across the interface. Now, for a glass air boundary, that's about 42 degrees. So let's just go through a couple of examples to make sure that I can, my words have actually made some sense. So here's a prism. It's a semisphere, yeah. Light's coming in here, so that's the angle. It's hitting this, because it's nice and round. As we change the angle, it's always, the angle of incidence is always going to be 90 degrees, and so it goes straight through this interface. So we don't have to worry about this interface at all. This is the interface that we're worried about in terms of refraction and reflection. So this here is now hitting here at 35 degrees, and because it's going from more dense to less dense, now that's the other thing it doesn't mention, is that to get total internal reflection, the light beam only gets reflected into, or within is probably a better word, the more dense material. So it's got to be a boundary that's optically more dense to less dense, and so this is air. And so this beam would get refracted, and you can see now that even at 35 degrees, the angle of refraction, which is this angle just here, is quite large. And this is what we mean by the reflected beam. It's just bouncing off this interface, because this interface isn't perfect, and light recognizes that, and so some of it bounces off. Now, if we increase this angle to around 42 degrees, the light comes in, there's our angle of incidence, and the refracted beam only just gets out. And it's nowhere near as strong as it used to be, because most of the light is actually getting reflected. And so if you added up the intensity of these two beams, it would add up to this beam. And if we go past what's called the critical angle, so 50 degrees, none of the light is transmitted and all the light is reflected. Yeah? And that would be when we get total internal reflection. So anything over 42 degrees. So wherever the critical angle is the angle where the angle of refraction is actually 90 degrees. If we go back, what they should have done here is this line, let's draw it in nice big. If this is the critical angle, the refracted light is actually travelling along the interface between the glass and the air, and so that would be referred to as the critical angle. If that's the angle of incidence, this, recognizing that that's the normal, so this would be the critical angle, sometimes given as a C, and that would equal 90 degrees. So the critical angle is when the angle of refraction is equal to 90 degrees. Let's just move on and show you some more examples of that. Probably don't need our pen as big. Right, we've done that. So here we're going from water to air. Remember, we're going from more dense to less dense. We don't get total internal reflection going the other way, because it can't happen. The angle of incidence, because we're bending away from the normal, we can get an angle of refraction 90 degrees. But if we're going the other way, because the beam is bending towards the normal, we can never get the 90 degrees. Sort of makes sense. Well, it does make sense. It's just the way I'm explaining it. So here we move on. We're increasing this angle. So what's a nice colour? Let's go green. Yeah. So here we've got an angle. This angle is now increasing. And so this angle here is also increasing. And this angle is going to be bigger than this angle because we're going from more dense to less dense. Now if we move on, now we've hit the critical angle. So that would be referred to as the critical angle, because here the angle of refraction is equal to 90 degrees and the beam is travelling along the interface, and you can actually see that happening in the right situation. Now remembering there would also be a beam which isn't really shown that's reflected, and there'd also be one here, and there'd also be one here, which are just left out of the diagrams because they get a bit noisy. And then if we go past the critical angle, we get total internal reflection, and it doesn't matter, we can move this beam, this angle, any angle beyond the critical angle, and we get total internal reflection. And if we had another interface down here, alright, so if we actually had an interface there and these two surfaces were parallel, this beam, because it's now hitting at the interface at an angle of incidence which is, let's say, greater than the critical angle, this beam must reflect. And so if it keeps hitting interfaces, it will keep bouncing along on and on through the medium. And that's what we do with fibre optics, and we'll talk about that in a sec. Alright, now did I just make something disappear? I don't know, probably did. Alright, let's move on. Why is that down the bottom there? Let's get rid of that. Oh, my poor computer's having a breakdown. There we go. So, critical angle when the angle of refraction is 90 degrees. Another example, here we've got a torch. Now this is showing, if you've ever been scuba diving or swimming in a pool with some goggles on, it's why when you look straight up you can see people. Say you're on the swimming underwater at the edge of the pool, you look up, you can see people looking down at you. But if you try and look into the distance, you can't see anything. You just get a whole lot of reflections off the surface of the water, and the reflections are what's actually underneath. And it looks quite weird, but that's why, because you're trying to look at an angle greater than the critical angle, but no light can get through for you to see. Now, according to Snell's law, which is what we're using because we're talking about refraction, we can apply Snell's law, recognizing that the angle of refraction for a critical angle just has to be 90 degrees. What's the sine of 90? It's going to be 1. Now, let's do a couple of examples. So light, in this case, is going from light flint glass to air, and then also light flint glass to water. Now, in the first example, they've taken Snell's law and they simplified it. Because sine 90 degrees is 1, and the refractive index, or the absolute refractive index of air is 1, we end up with this. And there should just be a little divide by sign there that hasn't appeared, and so that's all they've done there. But basically they've used Snell's law, and if we go to the next one, you can see how they've used Snell's law, and that's the way I would recommend doing it, is always just start with this Snell's law, recognizing that for the critical angle we put in 90, we put in the two refractive indices because we'll be given those hopefully, or we might be given the angle and we might have to work out what the refractive index. Either way, we could cope with it, rearrange it, and we find out that it's 57.3 degrees or 39 degrees in that case. But treating each interface as it has its own critical angle. Now, what are some uses of it? Well, prisms are used in things like periscopes, but also in cameras. If you have an SLR, usually there's a chunk above between the eyepiece and the film, and that's got a prism in it because it allows the image to go through the lens, bounce off a mirror, then into the prism, and then into your eye. But periscopes also use them. You could put a mirror there and a mirror there, but a prism works just as well, and in some cases better. But some binoculars use prisms as well. Fibre optics. Now, in fibre optics, which are being used all over the place now, the National Broadband is making a network of fibre optics because it's the fastest, most efficient way to transmit massive amounts of data. Because what the advantage it has over copper wire is copper wire relies on sending charges, and there's a lot of leakage and a lot of loss due to resistance. Plus, it's not as fast because the transmission is not at the speed of light, and therefore you also can't cram in much data. It's harder to send multiple streams of data down one piece of copper. Can be done, but it gets more and more complicated, and a single strand of copper wire has a load limit of how much data you can put through it. Whereas a fibre optic cable, because you can send signals as digital light pulses, you can send multiple streams, and you can have multiple streams of data going both ways because the light will just go through each other without interfering. So that's why people rig up their houses with fibre optics, but we're also getting a fibre optic network across Australia. But it's also why you have computer systems use them in networks. So what is it? Well, it's a piece of glass, and the glass is silicon, and it's wrapped in, usually it's wrapped in plastic, and so you have a transition from more dense to less dense material. This case they're showing it as layers of glass, but it doesn't have to be glass, it just has to be something less dense than the actual fibre optic cable. Then it's usually wrapped in Kevlar and aluminium foil and all sorts of things just to make it a bit tougher. You can bend it, and you think, well, glass would break, but glass, very thin pieces of glass can be bent, and if it does shatter, because it's all wrapped up, the break doesn't actually open up and form a gap, and even if it forms a very small gap, the light travels through it because it just goes through it without much issue. So it still works. And so that's how they work. Light gets shone in here, hits this interface at greater than the critical angle, so bounces off, then has to hit this interface at greater than the critical angle because these two sides are parallel, and so forth. Even if you put some bends in it, the light will not get transmitted because the critical angle is so small, because they dope the glass as well. So we use this not just for data, but also for things like endoscopes, where surgeons go in and use pinhole surgery. The actual endoscope would be a fibre optic cable, and either has optics so that you're looking straight through it, or it's transmitting it through a camera through a fibre optic cable. Either way, still using total internal reflection. And this is just saying how the signal's sent down. You get electrical signal, it becomes light pulses, those pulses are sent down, and then they're deciphered, and you get a signal, and they can go both ways. You can send multiple strands, you can send different colours. Usually these pulses are laser light, so it's very coherent and a very efficient way of sending data, massive amounts of it. So now you should be able to do those questions in your workbook and all the other questions that I've asked you to do. So let's just quickly recap some of the real life applications of light as a wave. Flashlights, headlights, searchlights, yep, hopefully you understand that. Periscopes, I forgot to mention when we were talking about periscopes that some of the little cameras, like in your mobile phone, and also some of the point and shoot cameras, when you zoom in and out, some of the older cameras, when you zoom out, a lens comes out the front and goes backwards and forwards, But nowadays you can buy cameras that when you zoom in and out, no lens goes backwards and forwards. Instead, it's actually like the lens is a periscope, and the lenses are actually moving within the body of the periscope, and you don't see any change to the outside of your phone or your point and shoot camera. Not to be confused with some cameras that when you zoom, all they do is crop off the sides and make the picture look bigger, but you're not getting the same resolution. Bit hard to see nowadays, but you can fall for that sometimes. Telescopes and microscopes, clearly uses of light, refraction, Snell's laws, all those sorts of things. Telecommunications, we were just talking about. Endoscopes for surgery, just talking about. Sometimes when you look at the moon, you see a halo around it, and that's because of ice crystals in the upper atmosphere, and again that's a result of refraction. Have a look on winter nights, you'll see that. Rainbows, we've talked about. Sundogs, I've mentioned, and I'm just about to show you a picture of a sundog, if I can find it. Here it is. So this is taken down in Antarctica. There are icebergs, there's the sun, there's ice in the air, and these are little rainbows, which if I blew it up some more, but I can't, you would see these little rainbows either side, and they're called sundogs. So you see them in the northern and southern hemispheres where you go to the colder climates. Now let's get back to the thing. Salinometers. Looking at the how do you say that? Salinometers. Yeah, saline. Basically, saline gives it away. Looking at salt, so you can use optics to actually work out how much salt is in water. Twinkling stars we've talked about because of refraction from the Earth's atmosphere. Holograms are something that we haven't had to talk about, but you do see holograms on your credit cards and various other things, and they're a result of using light as a wave. Lens coatings, if you've got glasses, you can have some coatings that actually help you get rid of glare. Some photographic lenses also use lens coatings. Interferometers, they are also used for measuring concentrations in solutions. Element identification, we can use that if you heat up any element, you can get light from it, and you can identify what it is from the electron orbitals. And crystal identification, remember we talked about X-ray diffraction. And 3D movies rely on light and the way that we perceive it and how it's actually broadcast. Again, not in our course, but you're welcome to look into it. And your LCD TVs are all a result of polarization and refraction. So that ends our topic, light as a wave, and in the next one we're going to learn about light as a particle. So see you later.